Okay, so question number 6 on this problem set is explain why regulation of pyruvate dehydrogenase is critical for controlling the flux of the citric acid cycle. So I'm going to explain to you this answer and also a little bit more about anaplerotic and cataplerotic reactions here. So one model for the citric acid cycle that found very helpful talking to various students in the class is to think of the citric acid cycle as a water wheel. So with the water wheel, our wheel basically has paddles or buckets on it, um, and the water basically pours onto these, filling them up, and then they dump the water out at the bottom, and the wheel spins. All right, this is very analogous to the citric acid cycle. So the wheel and the paddles on the wheel are kind of analogous to the carbon inside of the cycle. So an anaplerotic reaction is basically going to add on another paddle wheel. A cataplerotic reaction is going to pull a paddle wheel off. All right, so if we had exclusively cataplerotic reactions, eventually our wheel would have no paddles, and this wheel would no longer be able to turn. So we need both the paddles and the water falling on it in order for this to occur. Now, what is the water in this model? Well, the water is our acetyl-CoA. All right, it basically enters into the cycle very briefly, all right, and then leaves in some other form. And by entering in and leaving, it is actually driving the pathway in one direction. All right, and so it's doing this, in our case, in chemical terms, by Le Chatelier's principle. If you're adding on reactants, you're going to shift the cycle toward that reaction towards products. So by adding in acetyl-CoA, we're going to make more citrate. Right? We're going to push the reaction towards citrate, which is going to tend to now start spinning the cycle. All right, likewise, if we're losing products, which we're losing CO2, that is going to tend to pull the reaction towards products even more. All right, so the end result of this is if we have lots of acetyl-CoA, we increase the forward direction of the citric acid cycle. Now, what is flux? Right? I know the word flux confuses a lot of people. It confused me when I first learned about it. All right, well, it's simply just the forward reaction minus the reverse reaction. So what we're talking about here is just affecting the forward reaction, and you don't even have to really be concerned with the reverse reaction all that much. Mainly because, well, CO2, once it leaves, it's not going to come back on. It's very hard for nature to actually fix CO2. It basically leaves and we exhale it. And so the reversal reaction is essentially dead for all intents and purposes. So how can we control the rate of this cycle then? Well, we can control it in one of two ways. One, we can control the paddles themselves. All right, so anaplerotic reactions will tend to speed up the cycle because we're adding more paddles. Likewise, cataplerotic reactions will tend to slow it down. All right, the other main way we can control it is by controlling the water flow. So if we have lots of acetyl-CoA, we are going to speed up the cycle. Likewise, if we have a little trickle of acetyl-CoA, it's going to move much more slowly. And how is acetyl-CoA produced? Well, pyruvate dehydrogenase. So if we can regulate pyruvate dehydrogenase, we can regulate the entirety of this cycle.